And once it's there, you gotta get some. That'll do it. All right. I think maybe the best way to do this is to start with the total amount of volume of water that is fallen. So we have 70 square miles times 1/2 inch. All right, you can write those both over one if you want. That would give us the volume. Obviously, our units aren't good yet. You either need to convert everything to miles or everything to inches. Since we have 2 millimeters here, let's go ahead and do inches. So we could say there are square miles on the bottom, square feet on the top, 5,280 feet in 1 mile, since we're talking square feet. You want the square. So those will cancel. And then we can say there are 12 inches in a foot. And again, we want squares, so square feet cancel. So that would give us the total amount of water that has fallen in cubic inches. If I got that, there's what I'm calculating. A lot. 10 to the 11. I buy it. Cubic inches. Yeah. Then we need the volume of a raindrop. We have 4/3 times pi r cubed. The radius is 1. 1 cubed is still 1. That would be millimeters. We want inches, so we know there are 10 millimeters in 1 centimeter. Cube, cube, cube. And we have 2.54 inches or centimeters in an inch. And that would give us the volume of a raindrop measured in cubic inches. And then what would we do with those two numbers? Then divide them. All right. It would be this amount of cubic inches. Really, we would be multiplying by raindrops per cubic inch. And that would tell us the number of raindrops, right? So whatever we get here, I don't know what that number is, it's right there. So divide it, and that would tell us the number of raindrops. Hopefully, we should be able to maybe get 5.5 times 10 to the 14 raindrops. Any questions on what we did there? A lot of new analysis. If you can do that, then you can do any of it. All right, let's get into today's lesson. Objectives for today. First of all, to define force, explain the difference between scalars and vectors. All stuff is done before, hopefully, in modern physics. So we'll talk about force. We'll talk about adding vectors graphically. We'll get into vector addition algebraically as well. And then we'll start talking about Newton's law, the first and the third laws of motion. And I think the last one deals with our some vectors algebraically. So both graphically and algebraically. Almost always we'll be doing it algebraically. We'll just kind of take a look at what it looks like if you have this graph. All right. So first objective is to define force, talk about scalars and vectors. What's a force? It's a Newton. Okay, yes, I units are Newtons. There's a typo there. 1 Newton is 1 kilogram meter per second squared. And times acceleration. Force is action Push or pull on an object. Right? Something pushing, something pulling an object, causing it to. That's why we take the block. What's the difference between a scalar and a vector? A vector has direction, good. A vector has direction. A scalar is simply a magnitude. What's magnitude? Good. How big something is, how large something is. And the vector not only has magnitude, but direction. It is a vector, good. If something is being pulled 4 newtons to the east, that is going to be significantly different than if it's being pulled 4 newtons to the south. So force is going to be a vector. What were some examples of scalars? Color. Distance traveled is a scalar. Good. Distance traveled would be a scalar. What else? Time, yeah, you would say that something took 4 seconds to the east. Only a magnitude that only has the 4 seconds part. Yeah, that's a different type of second, so that's not a time second. You're right. Well, longitude, latitude, like they have however many degrees in that minute second, but that's a fraction of a degree. That's not like a unit of time. Those big ones, real big ones. Mass, kilograms, and you wouldn't say that something has a mass of 2 kilograms flat. Lots of things that are vectors: velocity, acceleration. Speed is a scalar, velocity is a vector. So if it has direction, technology is a velocity. Speed at how fast, velocity at how fast can the district. All right, so we just kind of talked through these. I don't want to take the time to go over them all. Defining force is a push or a pull. Difference between a scalar and a vector. Scalar, magnitude only, vector, also direction. We just talked through several examples of each. Speed, time, mass are all scalars. Velocity, acceleration, force would all be vectors. All right. In order to add vectors rapidly, we add them by what we call tip to tail. All right. So we have 3 vectors on each one. Those are actually the same 3 vectors. All right. This vector, that one, and this vector right down here are all exactly the same. They're the same length and the same direction. This one looks like it's due south. We'll do straight down, and then we have one here. All right. Notice no matter which order I add the vectors in order to add them tip to tail, you start with one vector, and then the tip of that tail starts at the tail of the other one, like that. Right? We did do this last week. And then this one here would go right there. All right. So I added those 3 vectors together. The resultant is basically what the answer is when I add them together. Right? In order to get the resultant, where do I start? From the beginning, and I go to where I ended, right? So that would be my result. All right. What if I switched around the order that I added it? So I start with this one, maybe. Same magnitude, different direction. Any other ideas? Everybody agree? Might be exactly the same. Might depend on which side the axle. So I switched around the order. I did the down one first, and then the up to the right one. And then all right, notice if I connect them here. Looks like it's about the same, doesn't it? Suppose I can get a ruler out just to measure the angle. Should be exactly the same. All right. Notice if I switch the order around again, I go this one first, and then maybe the one that goes down, and then the one that goes over here is going this way. And it again gives me exactly the same thing. Same direction, same size, exactly the same thing. So it doesn't matter which order we add vectors in. That's called commutative. Right? And vector addition is commutative. It doesn't matter. You can switch around the order that you add the vectors. Obviously, we're not going to be doing it algebraically or graphically very often, but algebraically it works the same way. You don't necessarily have to add vector 1 plus vector 2 and then add that to vector 3. If it's easier to do 1 and 3 together and then get 2, or just simply add them all together to begin. Questions on that? That's really about all we do with adding them graphically. There's not a whole lot to do. Other than using a protractor and a ruler, it makes a lot more sense to do it algebraically and break it down. All right. Newton's laws. Newton's laws. What does inertia mean? You disagree with the fact that Isaac Newton's a man? No, I was talking oh, really? Yeah. So you know it. Yeah. It's that. You don't have to talk about it. That's one more date that I don't. What's inertia? It does have to do with mass. Yeah, it's an object's resistance to move. Obviously, then that's one. Right? It's the tendency of an object to maintain its motion, and then unless an external force acts on it. So, an object wants to keep its motion, wants to maintain its motion. So, if it's stationary, if it's motionless, it doesn't want to move. If it's moving at 5 meters per second, it wants to continue moving at 5 meters per second, unless another force acts on it. Isaac Newton is absolutely a man, because in 1587, what did he do? Yeah, he wrote that book, which states his great laws of motion. Three laws of motion. I want to talk about laws numbers 1 and 3 today. The first law is also called the law of inertia. Therefore, what does it say? It doesn't necessarily state, yeah. I mean, it states it as a law, though. An object that is motionless will remain motionless, and an object that is moving maintains its motion unless acted upon by an external force. Right? If we don't have an external force, therefore velocity won't change. The net force acting on the object will be. An object at rest will remain at rest. An object in motion will maintain its motion until acted on by motion. No, that was the answer. All right, 4 examples in this class. Instead of having you write all the examples out, I photocopy them, so you don't have to write them all down and copy them off the board. The question is where I put them.